Hello everyone. I'm honored to be here at the 6th International Conference on Intelligent Systems and Computer Vision. My name is Abla Rahmouni and I'm thrilled to present our article entitled Fine-Tuning Vision Transformers for Enhanced Skin Lesion Classification, Navigating the Challenges of Small Datasets. This article co-authored with my supervisor, Professor Sbari Moulay Abdelwahed and Professor Arab Abdullah. I want to express my gratitude to my supervisor, Professor Sbari Moulay Abdelwahed, for his invaluable guidance and support throughout this research journey. And thank you all for joining us today. Your presence is greatly appreciated, and I'm excited to share our findings with you. Without further ado, let's dive into the details of our research and explore the insights we've uncovered together. But first, we're gonna start with an introduction, and then we will explore the or some existing literatures in which we're gonna have an overview of pre-trained models and pre-training in natural language processing as well. Then we're gonna move to the explanation of the architecture, in which we're gonna see the used data set, pre-processing and augmentation, the model architecture and fine-tuning as well, evaluation metrics. And after that, we're gonna explore the results obtained performing on the PH2 data set, and we will end with a conclusion and perspective, of course. So cancer is the most common form of cancer globally, with millions of cases diagnosed each year. Yet, accurately identifying and classifying skin lesions remain a significant challenge for clinicians, frequently resulting in delays in both diagnosis and treatment. So, why is classifying skin lesions is important? It is important for the following reasons. Firstly, early detection. When we talk about early detection of skin cancer, this significantly improves patient outcomes. Proper classification of skin lesions allows for timely diagnosis and treatment, potentially saving lives. Also, treatment planning. Accurate classification helps clinicians determine the most appropriate treatment plan for each patient, whether it's surgical, intervention, medication, or other therapies. Also, one of the important reasons is prevention and education. So when we talk about prevention and education, we can say that understanding the types of skin lesions can aid in preventive measures such as sun protection and regular skin checks. It also facilitates patient education about skin health and cancer risk factors. So what are the challenges? Let's talk about the challenges. We can mention about the challenges that face clinicians in accurately diagnosing skin conditions. We can mention visual similarities, because many skin lesions exhibit similar visual characteristics, making it challenging for clinicians to differentiate between benign and malignant lesions based on visual inspection alone. We can mention also subjectivity. Diagnosis based on visual examination can be subjective and prone to errors, as it relies heavily on the clinician's experience and expertise. And most important challenge is time constraints, because clinicians often have limited time for patient consultations, leading to rushed assessments and potential oversights of important diagnostic clues. By artificial intelligence and machine learning to these challenges. And we are gonna talk especially, or we are gonna mention especially the automated analysis, because artificial intelligence and machine learning algorithms can analyze large data sets of skin lesion images, enabling automated classification with high accuracy and efficiency, the augmented diagnosis as well. These technologies can serve as decisions support tools for clinicians, providing additional insights and enhancing diagnostic accuracy. And continuous improvements as well. Continuous improvements mention that in machine learning models can continuously learn from new data and refine their classification abilities over time, so potentially improving diagnostic accuracy and reducing errors. Well, now that we have finished with the intro, which is exploration of existing literature, here we are gonna have an overview about pre-trained models. So pre-trained models have emerged as a powerful paradigm in machine learning, offering pre-trained parameters and architectures that can be fine-tuned for specific tasks. These models are typically trained on large-scale datasets to learn general features and patterns, enabling them to capture complex relationships within the data. The goal of our work is to explore the effectiveness of fine-tuning vision transformers for improving skin lesion classification accuracy, particularly when faced with the challenges posed by small datasets. So, to address the challenges in skin lesion classification, our study focuses on enhancing the performance of machine learning models using vision transformers. Here we have an example of a model that can be fine-tuned on other tasks. As mentioned in this figure, the top row refers to the original task that AlexNet was trained on, which is classifying natural images into different categories using the ImageNet dataset. The bottom row indicates that the parameters or the learned numerical values of layers in the AlexNet model are being reused for a different task. Concerning the pre-training in natural language processing, it refers to the process of training a model on a large dataset using unsupervised learning techniques before fine-tuning it on a specific task. During pre-training, the model learns to understand the structure and meaning of language by processing vast amounts of text data. This allows the model to capture various linguistic patterns and relationships, making it more effective and performing downstream NLP tasks such as text classification, sentiment analysis, and language generation. Pre-training is a key step in building powerful NLP models that can achieve high performance across a wide range of applications. Two examples. The first one is BERT, which has been trained on a large corpus of text from different sources like Wikipedia and books. It learns to predict missing words in a sentence, mixed language modeling, and to determine whether two sentences follow each other logically, so it can be fine-tuned on specific NLP tasks such as text classification and question answering. Adaptability is another example of a pre-trained NLP model developed by OpenAI. It's trained using a transformer architecture on a diverse range of text data. GPT learns to generate coherent and contextually relevant text by predicting the next word in a sequence of text. It can be fine-tuned for various tasks, including text completion, text summarization, and language translation. Now we're gonna move to the approach or the architecture explanations. But first, let's have a look on the used dataset. So we've worked with two different datasets. The first one is the ISIC 2020 dataset, which is a huge dataset, and the second one, or the one that we've used for the fine-tuning, is PH2 dataset. In comparison with the first one, the PH2 dataset is really more smaller than the first one. So here in this table, we have the first row shows the examples from the PH2 dataset, and the second row shows some examples from the ISIC 2020 dataset. The first pair shows the melanoma, examples of melanoma images, and the second pair shows examples of non-melanoma. The dataset of ISIC 2020 comprises or contains 33,126 dermatoscopic training images, showcasing various benign and malignant skin lesions observed in over 2,000 patients. These images are also represented in the RGB, red, green, and blue color space, with a resolution of 767 by 1022 pixels. Concern includes a total of 200 images with 116 benign and non-melanomas and 14 representing cases of melanoma skin cancer. These images are in the RGB color space as well, and they have a resolution of 764 by 575 pixels. About the pre-processing, during the pre-processing, we undergo several steps such as resizing images to 72 by 72 pixels and partitioning the input image into smaller patches. That ensures that the data is in a suitable format for the classification tasks. And operations such as rotation, flipping, and zooming, which enhances the diversity and quantity of training data, helping the classifier generalize better to unseen examples and reducing the risk of overfitting. Model architecture and fine-tuning. So inspired by vision transformers for image classification, our model architecture incorporates transformer blocks. These blocks include multi-head self-attention mechanism designed to capture intricate dependencies within dermatoscopic, and here is the architecture of the original ViT applied for skin lesion detection. The image, as you can see, the input image is divided into small fixed patches. Each patch is then linearly projected to a lower dimensional vector called the patch embedding. These patch embeddings are treated as words or tokens and become the input for the transformer model. After the patch embeddings have been processed by multiple transformer layers, the final layer's output is passed to the classification head, which is MLP, or multilayer perceptron. The classification head is responsible for taking the encoded information from the transformer and mapping it to the desired output for the specific task at hand. Fine-tuning. Well, fine-tuning unfolds a systematic sequence commencing with transfer learning, where initial predictions are obtained directly from the pre-trained model on the dataset. Subsequently, a staged fine-tuning process ensues. In the first stage, only the multilayer perceptron undergoes training, allowing the model to adapt to the specific nuances of skin lesion features. Building upon this, the second stage extends fine-tuning to all layers of the vision transformer model. This comprehensive approach refines the model's representations, aligning them precisely with the intricacies of the PH2 dataset. The strategic fine-tuning stages contribute to the model's heightened sensitivity to dermatoscopic patterns, ultimately enhancing its efficacy in skin lesion classification. Well, those are the evaluation metrics used. Accuracy, which we measured the overall correctness of the model's predictions, and then the confusion matrix, recall or sensitivity, and then the F1 score. So it highlights the proportion of actual positive instances correctly identified by the model. This metric offers a balanced assessment of the model's performance, considering both false positives and false negatives obtained results. But before to talk about the results, I want to mention that the pre-trained model have been limited to one epoch due to the dataset's enormity, of course. Because as we saw in the description of the ISIC 2020 dataset, the dataset contains over than 33,000 images. So those are the results. The results presented in this table showcase the performance of the models on the small dataset PH2. Initially, we've tried with the ViT applied from scratch, which gives a 77% of accuracy. Then we moved to work with the pre-trained model, which we train on ISIC 2020 datasets. The initial foray into transfer learning gives 73% of accuracy, while transfer learning only the MLP or the multi-layer perceptron significantly boosted the accuracy to 83%, and encompassing all layers yield the highest accuracy at 85%. Conclusion. So to conclude, I just want to mention that our exploration into the realm of vision transformers, ViT, in dermatology unfolded announced interplay of transfer learning and fine-tuning strategies. The initial foray into transfer learning from an ISIC 2020 pre-trained model limited to one epoch due to the datasets. Fine-tuning played a pivotal role in refining and boosting the power of the model, even with the challenges of the small datasets like PH2 dataset, which came to the forefront, requiring a delicate balance to avoid overfitting and underfitting. And thank you for your attention.